The order comes over the rescue radio. Do not touch the water. In a flooded city, that order is almost impossible to obey. Captain Naomi Boudreau is guiding a shallow draft rescue boat through a New Orleans neighborhood when she sees a man trapped on a porch. The current has pinned a fallen fence across his steps. Water reaches his waist. Naomi brings the boat close and extends a pole. Something long rolls beneath the surface. The man's legs lock. His hands close around the railing so violently that his knuckles whiten. Then he falls face first into the flood. Naomi's partner grabs his jacket and pulls him over the side. The man coughs, alive but unable to explain what happened. He says the water punched every muscle at once. A second pulse strikes the metal pole in Naomi's hand. Not enough to throw her across the boat, not enough to stop her heart, but enough to make her forearm contract and release it. The pole sinks. A thick serpentine fish rises for air beside it. Electric eels have entered the flood. The name is misleading. Electric eels are not true eels, but South American knife fishes belonging to the genus Electrophorus. They evolved in warm freshwater systems where visibility can be poor and dissolved oxygen low. Much of their elongated body contains specialized electric organs built from thousands of modified cells. Activated together, those cells create pulses used for navigation, communication, defense, and hunting. Different electric eel species produce different maximum voltages. One species, Electrophorus voltae, has been measured near 860 volts, the highest reported electrical output of any living animal. But voltage alone does not tell you what happens to a human. Current, duration, pulse pattern, distance, body position, water chemistry, and the path through tissue all matter. An eel is not a power station. It cannot energize an entire street. That fact becomes the first rule of survival. The invasion begins when a hurricane damages a private aquatic facility near an industrial canal. The collection includes several adult electric eels and younger animals kept for display and research. Floodwater tears through the building, mixes tanks with drainage channels, and carries the fish into the city before anyone completes an inventory. Most would face terrible conditions. Electric eels are freshwater fish. Storm surge can bring saltwater inland, and rapid salinity changes create a major physiological challenge. Cold water can slow them. Strong currents can sweep them into unsuitable habitat. Contaminants may injure them as easily as native fish. But a New Orleans flood is not chemically uniform. Rainwater, canal water, sewage, storm surge, and runoff form shifting pockets. Some streets may become brackish, while others remain comparatively fresh. Pumps, walls, levees, and elevation trap water in separate basins. The eels that enter the wrong pockets die. Those reaching warmer, low salinity drainage canals and flooded neighborhoods may survive for days or weeks. Low oxygen does not eliminate them. Electric eels breathe air at the surface and can tolerate waters that suffocate many fish. Every rise for breath reveals them for a moment, then the water closes again. Naomi reports the encounter. Dispatch initially suspects a damaged electrical line. That is the correct assumption in nearly every urban flood. Downed utilities, submerged wiring, unstable structures, contaminated water, current, and hidden debris remain far greater threats than exotic fish. Utility crews isolate the local grid. The shocks continue. A wildlife team places underwater cameras near the damaged facility. One recording shows an electric eel approaching a cluster of displaced fish. It emits brief high-voltage pulses. The prey twitch involuntarily, revealing their position. A rapid volley causes muscle contraction long enough for the eel to seize one. The footage confirms both the species and the mechanism. Electric eels use weak electrical signals to sense their surroundings. Objects with different conductivity distort the self-generated field, helping the fish navigate when sight is limited. They do not track human body heat, listen to household appliances, or map a building like a supernatural radar. Stronger pulses can make hidden prey move. That movement provides information. Inside floodwater filled with debris, the ability is formidable. A fish can locate prey around submerged furniture and beneath vegetation. Yet the same clutter blocks movement, divides water, and can trap the eel in basements or courtyards. The danger to people remains local. Electrical energy spreads through water and weakens with distance. Dissolved salts increase conductivity, but that does not turn every nearby car, fence, and handrail into one citywide circuit. In more conductive water, current may be shunted through the surrounding water rather than forced through a distant human body. Metal can change local current paths, especially when it forms a continuous contact. But isolated vehicles do not connect entire blocks. The nightmare is smaller than the original rumor, and therefore harder to see. A rescuer waiting within a few feet of an eel may receive a shock. Someone reaching into a trapped pool can bring a hand close to one pole of the electric organ, while the rest of the body completes a path through water. A frightened eel can discharge repeatedly. Muscles contract. Balance disappears. The victim falls into water filled with broken glass, fuel, sewage, and current. Drowning is more plausible than instant electrocution. For people with heart conditions, implanted devices, or prolonged close exposure, additional cardiac risk cannot be dismissed. But the claim that every full-strength pulse automatically causes ventricular fibrillation is not supported. Some people have survived multiple electric eel shocks. The responsible warning is not, "The flood is one lethal battery." It is, "An unexpected muscle contraction can kill you when your face is inches above the water." That warning changes rescue operations. Teams stop unnecessary wading in affected sectors. They use non-conductive poles where practical, maintain distance from surfacing fish, and mark isolated pools. Boats are not automatically death traps because they have aluminum hulls. A metal hull can conduct, but occupants sitting inside are not necessarily placed across a dangerous voltage difference. The higher risk moment comes when a rescuer bridges boat, water, equipment, or victim with wet hands. Every rescue becomes a problem of contact. Naomi returns to the porch where the man fell. Wildlife officers deploy a net barrier at the end of the block. The eel surfaces near a submerged car, and a handler attempts to guide it into a capture container. The fish rushes the obstacle, raises part of its body from the water, and presses against the wet frame. This behavior has a biological basis. Electric eels can lift themselves partly out of the water during defensive encounters, bringing their electric organs closer to a target and increasing the effective shock as more of the body makes contact. What looks like a leap is not flight. It is a way to concentrate an electrical field. The handler releases the frame before the eel reaches his hands. The animal is captured on the second attempt. It is only one of the missing adults. As reports spread, social media transforms a localized hazard into an electrified apocalypse. Maps mark entire neighborhoods as instantly fatal. Videos of downed power lines are labeled eel attacks. People fire weapons into floodwater. Others attempt to catch the fish for online attention. One amateur drops bait into a flooded parking garage and ties the line around his wrist. When an eel strikes nearby fish and the man reaches into the water, the contraction pulls him off the ramp. He survives because a companion is close enough to drag him out. The animal never targeted a human. Human curiosity completed the circuit. Native wildlife suffers for the same reason. Residents kill harmless American eels, bowfin, gar, and large catfish after mistaking them for the invader. Electric eels can be distinguished by trained personnel, but muddy water reduces every fish to a shape, and every shape to a threat. Meanwhile, the real eels follow prey into quieter flood zones. Rodents and pets struggling in the water create movement, but electric eels are primarily adapted to capturing fish and other manageable prey. They do not form packs to hunt stranded people. Most species and populations are considered largely solitary, although remarkable group hunting has been documented in Volta's electric eel under particular conditions in the Amazon. In that behavior, Many eels herd schools of small fish, and smaller hunting groups release nearly simultaneous volleys. It does not mean any collection of displaced electric eels will instantly coordinate. It does not combine their voltages into a single blast capable of electrifying a crowd. At most, several fish discharging in the same confined pool could create overlapping, unpredictable pulses. That is enough. Floodwater recedes from broad streets into underpasses, drainage ditches, basements, and enclosed courtyards. The eels lose territory, but become concentrated. Rescue crews now know many of the locations, while homeowners returning after evacuation do not. Naomi accompanies a utility team into a hospital basement. The main electrical supply has been disconnected. Water remains below the stairs, separated from the street by a closed flood door. A worker sees movement beneath a floating cabinet and assumes it is a rat. Naomi stops him before he steps down. An eel surfaces for air. The basement is not connected to an entire electrified network. It is more dangerous. A closed freshwater pocket with one stressed animal and only a few feet between it and anyone entering. The team pumps slowly through a screened intake while wildlife officers remove the eel. This becomes the model for recovery. Divide the city into water bodies rather than treating the flood as one lake. Test salinity, temperature, and connectivity. Watch for obligatory surfacing. Screen pumps so animals are not shredded or transported elsewhere. Capture viable fish where possible. Assume conventional electrical hazards until the grid is verified safe. Then investigate biological ones. The pumps create another risk. If an eel enters an intake, it can be moved toward canals outside the original release zone. Discharging cannot destroy a municipal pump from a distance, but large fish can obstruct equipment or injure a worker during maintenance. Every removed volume of water changes the invasion map. Weeks pass. The city begins drying. Some electric eels die in saline pockets. Others are found stranded as water drains away. Several survive in freshwater canals where they feed on native fish. The emergency now splits into two timelines: immediate danger to recovery workers and long-term establishment in Louisiana waterways. Could they reproduce? Survival after a storm does not guarantee an invasion. A breeding population needs compatible adults, suitable nesting conditions, warm, fresh water through the year, enough food, and offspring that survive predators and seasonal extremes. The released collection may contain too few animals or the wrong sexes. Pollution and salt intrusion may prevent successful reproduction. But southern Louisiana also offers warm bayous, slow canals, abundant prey, air access, and long periods without severe cold. If even one breeding pocket forms in a connected freshwater system, eradication becomes far more difficult than removing animals from isolated streets. Native alligators, large fish, birds, and cold events would impose pressure. Electric discharge is a strong defense, not invulnerability. Juveniles could be eaten. Adults could be injured, trapped, or killed. The invaders would also compete with native predators for fish, rather than simply sitting above the food web. The ecological impact would depend on density. A few adults might remove limited prey and remain rare. A large population could alter fish communities, prey behavior, and food available to birds and native predators. No honest biologist could predict total domination from the first storm season sightings. The final missing adult is never recovered. Months later, Naomi visits a drainage canal beyond the original flood zone. The city is dry. Traffic moves across a bridge. Children watch minnows from the bank, while a wildlife crew checks a row of baited cameras. One camera recorded a long body the previous night. The image is too blurred for identification. Naomi waits. A fish breaks the surface, takes a breath, and disappears. The water does not hum. The bridge does not become electrified. Nothing dramatic happens. That is what worries her. The storm emergency ended when the streets dried. An invasion would begin only if the animal no longer needed the disaster. If electric eels escaped into a flooded New Orleans, should officials drain and chemically treat every isolated waterway to guarantee removal? Or protect native aquatic life and accept the possibility that a few eels survive? Tell us which risk you would choose in the comments. Subscribe to What If Animals and watch the next scenario. Because the most dangerous creature in a flood may not be the one that controls the whole water. It may be the one waiting in the only pool you have to cross.